Today, we are diving straight into the invisible rules that govern, well, absolutely everything that moves, bends, or breaks around us. We're unpacking the fascinating concepts from Science Standard 8, Chapter 8 on force and pressure. So, if you've ever found yourself wondering why the physical world behaves exactly the way it does, you are definitely in the right place. But before we get too deep into the physics, let's start with a little everyday mystery. How does a simple rubber sucker defy gravity to just stick to your wall? I mean, think about it. There's no glue, there's no tape involved, and yet it holds on with this incredibly strong grip. Well, before we wrap up today, we are absolutely going to solve this mystery, and you'll see exactly how the invisible forces all around us make it happen. To get to that answer, here is our roadmap for today. We'll start with the fundamentals of force, then look at how forces change things, move on to understanding pressure, explore liquids and gases, and finish up with some real-world applications. Okay, let's jump right into Section 1, the fundamentals of force. At its core, a force is actually incredibly simple to define. It is literally just a push or a pull acting on an object. But here is the critical part you need to remember. It's a vector quantity. That means it's not just a raw amount. It has both magnitude, which is the sheer size of the push or pull, and direction. Pushing a door closed is vastly different from pulling it open, right? So unlike a scalar quantity that only has an amount, with force, exactly where you aim it changes the whole game. Now, what's really fascinating is how these forces actually interact with things. We've got a clear split here. On one side, we have contact forces, which require direct or indirect physical touch. Think of the muscular force you use to lift a heavy box, or the frictional force rubbing against your car's tires to slow it down. But then, on the flip side, we have the wild world of non-contact forces. These are forces that act invisibly over a distance. An electrically charged object exerting electrostatic force, the Earth's gravitational pull keeping us grounded, or a magnet pulling a piece of iron. Literally no physical touch required. But here's the reality. In the real world, it is pretty rare for just one single force to be acting on an object at any given time. Usually there's a whole bunch of them. That's why we use the concept of net force. The net force is just the single force that represents the grand total, the ultimate sum of all the different pushes and pulls acting on an object at once. Let's put some quick numbers to this. If you have several forces acting on an object in the exact same direction, they just add together. So say you've got two forces, 10 newtons and 20 newtons, both pushing a block to the right. They join forces, literally, to create a total net force of 30 newtons. Now, if they were pushing in opposite directions with the exact same strength, they cancel out, and the net force would be zero.
Moving right along to Section 2, how forces change things.
So what happens when an unbalanced net force hits something? Well, it is incredibly powerful. It can wake up a completely stationary object and set it in motion. It can slam on the brakes and stop a moving object dead in its tracks. It can deflect something, meaning it completely changes the direction of an object's path. It can speed things up, slow things down, and honestly, perhaps most dramatically, it can even physically crush, stretch, or completely alter the actual size and shape of an object. Force literally dictates all motion and form. All right, let's pivot to Section 3. Understanding pressure. Here is the essential question to think about. If a force is just a push or a pull, how do we measure the intensity of that push when it isn't just hitting a single point, but is spread out over a huge, wide surface, or highly concentrated on a tiny little speck? And that brings us perfectly to the concept of pressure. Pressure is the exact measurement of a force pushing down perpendicularly onto a specific single unit of surface area. Basically, it's force, but contextualized by the physical space it actually occupies. To keep our measurements straight scientifically, we use different units for these two concepts. For force, our standard SI unit is the Newton. But for pressure, because we are dividing that force over an area, the unit becomes newtons per square meter. In the scientific community, this is famously known as the Pascal. So here is the crucial takeaway, the golden rule of pressure, if you will. Pressure is directly proportional to force. That makes perfect sense. You push harder, the pressure goes up. But it is inversely proportional to the area of contact. If you take that exact same force and spread it out by increasing the contact area, the pressure actually drops. A bigger area means less intense pressure, while a tiny area creates highly concentrated, extreme pressure. Okay, on to Section 4, liquids and gases. Now that we've got a handle on solids, let's look at fluids.
Unlike a solid weight that just presses straight down because of gravity, gases are wildly energetic. They exert pressure in absolutely every direction against the walls of whatever container they're trapped in. Up, down, sideways, it is constant omnidirectional pressure.
Liquids behave somewhat similarly, but with a catch. At any specific depth, a liquid will exert the exact same pressure in all directions. However, remember this absolute non-negotiable fact of physics. The deeper you go into a liquid, the more the pressure increases. All that heavy liquid above is bearing down, amplifying the pressure exponentially the further down you go.
This isn't just theory either. This is exactly why deep-sea submarines have to be engineered the way they are. Their hulls are made of exceptionally strong, massive, thick materials. If they weren't, they simply wouldn't have the structural integrity to survive. The tremendous, crushing pressure from the massive weight of the deep-sea water would crumple them like a tin can.
But hey, you don't actually need to be at the bottom of the ocean to experience immense pressure. Right here, all around us, we have atmospheric pressure. This is quite literally the massive weight of the ocean of air above us pressing down against every single surface. And because the column of air is tallest right at the bottom, atmospheric pressure reaches its absolute maximum strength right at sea level, steadily decreasing as you climb higher in altitude.
Let's wrap up with Section 5, Real-World Applications. Think about an everyday medicine dropper. When you use it, it feels like you're creating suction, right? But it's actually pressure at work. When you dip the nozzle and press the rubber bulb, you're forcing the air inside to escape as little bubbles. With that air gone, the pressure inside the dropper plummets. So when you let go of the bulb, the heavier, much stronger atmospheric pressure pressing down on the liquid outside violently shoves that liquid straight up into the low-pressure glass tube.
A medical syringe uses the exact same brilliant physics. You dip the nozzle into the liquid, you pull back the piston, and boom, you've just created a low-pressure void inside the syringe. Once again, the atmosphere does all the heavy lifting for you. The high atmospheric pressure pushing down on the surface of the liquid effortlessly forces it right up into the syringe.
And that brings us full circle to our opening mystery, the rubber sucker. When you mash that sucker flat against the wall, you are physically forcing out all the air beneath it. Because of that, the air pressure trapped strictly inside the sucker drops to almost nothing. Suddenly, the heavy, high atmospheric pressure of the entire room is acting exclusively on the outside of the rubber, pushing hard against it and pinning it stubbornly to the wall. No magic, no glue, just the incredible weight of the atmosphere.
It really makes you see the everyday world a bit differently, doesn't it? Which brings us to the end of this explainer, but before we go, I want to leave you with one final provocative thought. We just established that atmospheric pressure is this immense, heavy force, and it's at its absolute maximum right down here where most of us live at sea level. So considering the incredible, crushing weight of the atmosphere pressing in on you from all sides at this very second, what hidden internal forces are keeping your body from collapsing right now? Think about that for a while, and keep exploring the amazing science hiding all around you.